Okay, welcome to lecture 2. We talk about functions. First, some terminology. Functions are rules which give you from a number x a new number f of x. Let's just take an example of a function. So let's take f of x is equal to 1 over x. This is a function which goes to 0 at infinity and has a problem at x equal to 0, but it looks like that. So that's the graph, and we call this the graph of the function. And we have the x, and here y, and so that's y is equal to f of x. And then we have also the domain. So the domain A is where f is defined. Usually it's the whole real axis. In this case not. So in this case the domain of f is all the real numbers without and the range is the same thing. So this is in this case the range of f. So the range of f. This is all y which are reached by f. So in this case we can draw it like that. So the domain is everything here. So this is the domain here. And the range is everything which is reached. In this case, this is everything here, except 0. Usually we have to talk about the domain, like if we take the function square root of x, right? In this case, the domain r plus. So it's everything from 0 to infinity. So it's not defined for negative x. So we usually leave this domain away if it's clear that it's defined everywhere, but sometimes we have to actually talk about the domain and the range of a function. But the function is just a rule. So we have x goes to f of x. So that's kind of the modern way to look at the function, as a rule which maps as a real number to other real number, and the graph is a way to visualize the function. Cool. So that's the part 1. We will look now at a couple of examples of functions or classes of functions. Cool. Let's look at polynomials, the simplest functions. Among the polynomials, the linear functions are very important. Particularly the function f of x is equal to x. So then f of x is equal to x. So we can now also change this. For example, we can change the slope when we have a kind of make the slope bigger here. So this would be f of x is equal to 2 of x. We can also move it up or down. Say, for example, if I take this and I move it up here to 2 here. So in this case, it would be this would be f of x is equal to 2x plus 2. We can also shift it around, like, for example, let's take f of x is equal to x minus 1. So let's take this one. So f of x is equal to x minus 1. So the most convenient way to see this is for x equal to 0, x equal to 1. Here we have a root. The others had. You can always compute the root, right? In this case, the x equal to minus 1 is a root. So these are called roots. That's an important thing. It's a place where f of x is equal to 0. And for linear functions, these are linear functions. Or affine. generally one calls this affine, is if you have a function, you are all familiar with this, y is equal to mx plus b. So that's kind of the general way how we can write a linear function, where this is the slope and this is the intercept with the y-axis, x-axis, y-axis. And this is something you know from pre-calculus. But then we can look at more interesting functions like x squared. So f of x is equal to x squared. Very important function. Parabola. This is x. This is y. We have seen that already in the first lecture. Y is equal to x squared. And we can also modify here things. For example, if we can take x squared plus 1, right, that would be x squared plus 1. We actually move it up. Or we can also take the negative, kind of, for example, this would be y is equal to minus x squared minus 1. Right, if this would be minus 1 here, this would be 1. Or we can shift it to the left or to the right. Right, for example, in this case, when we have y is equal to x minus 1 squared plus 2, so we have here 1, 2, so that's a parabola which has been shifted by 1 to the right and shifted 2 up. So in this case, that would be the way. But in general, we would write just y is equal to maybe ax squared plus bx plus c. So that's the general form of a quadratic function. So it's important to have a repertoire of functions which are known, and the cubic function is also a prototype which is important. This function, which is let me just draw that here, cubic function f of x is equal to x cubed. It is very important a prototype, because what we have is we have a root at 0, but we have also kind of a flat point here without being a maximum or minimum. So we will see this function is an important function, will be an important function for us. And as before, we can move it up and down. Like we can, for example, take this would be x cubed plus 1, or we can shift it to the left or to the right. Right, so if we have, for example, this function, if this is 2, so that would be f of x is equal to x minus 2 cubed. Just kind of flat here. A flat point here. And it continues like that. You can look at aquatic functions. For example, that's a beautiful one. I like this one. So this is the w function. So this is x to the 4 minus x squared f of x. Very beautiful function. We see that function again and again. So this is called a aquatic function. So, but you can continue, you can make, with polynomials, you can reach an amazing variety of functions. That's the first part. Now let's look at exponentials. Okay, let's look at the exponential function. It's a very important function, definitely one of the most important in all of mathematics. So we write both either xx or e to the x. So both notations are useful. This is useful, for example, if you don't want to use superscripts, and but it's the same thing. So this function goes to 0 at minus infinity and goes up here to infinity very, very fast. It has at 0, it has the point 1. And we will actually define it as a limit of compound interest functions where h is very small. So we will actually define it as a limit, but it's something which is showing exponential growth. also important is that this function is never zero. It's never zero. There's no roots. We can also, important is if we negate x, so we get this function here, so we may take this function. So this is e to the negative x. So that was e to the x here. And we can also modify this in various ways. For example, we can shift it up and down. We can also multiply it. For example, if we multiply it with 2, we get just something which grows faster. So this is 2 times e to the x. No, that's e to the 2x. So that's kind of just, I just change here things faster. So this is e to the 2x. So what I wrote before is actually a different function. When we have 2 times e to the x, then we go here through 2. So that would be this function here. So if you multiply by 2. So this is 2 times e to the x. So that's a different thing. And so that's the exponential function. You should know some rules about some rules like e to the x plus y is equal to e to the x times e to the y. That's one of the important rules. Or another important rule is e to the x to the y is e to the xy. Other important rule. Or also very handy will often be this formula. So that's e to the x times log x. And log x is the ln x. It's the same. We will talk about the ln x just in a second, which will be the inverse function. By the way, if you want to get the inverse function of a function, you just reflect it at this line here, the graph. So the log will be this function here. But that's about the exponential, and so we have already seen the exponential in the discrete. For example, we have seen 2 to the x, which is actually 1 plus 1 to the x over 1. So that's kind of when h is equal to 1. So that's the function, also an exponential function. And we can actually write this as e to the x times log 2. So it's also an exponential function. So, but these functions will come back, especially once we start integrating and start differentiating. So if you invert the exponential function, we get the log. So the log of, if you take, the definition is like that. If you take e to the log of x, we should get x. And so log of x is the inverse of the exponential function. So what you can do in order to draw the log, you can draw the exponential function. And then you can flip it. So what we have is we just flip it at the x equal to y here. So what we get is we get this function. So that's the log function. And because this was 1 here, this is also 1. So we have, especially log of 1 is equal to 0. And we have also the notation is log of x. Another notation is ln x. Most mathematicians use log of x. Almost all programming languages use log of x. This is by some professional mathematicians called infantile, because it has historically never been used, and it's actually quite awkward. X. You want to, and it's also more error prone. You can read it as 1n instead of ln. There are so many disadvantages of that ln notation, but it is used, and we use it as just a synonym here. And we would use the log of 10 of x for the inverse of 10 of x. So 10 of 20, that would be 20. But the log of e to the 20, that's 20. So what the log does, it reverses the exponential function here. So it's the inverse of the exponential function. So this is a very, very important function. And you are free to use ln x, I don't mind, even though it's infantile, but you can use it. It's also the only notation which has only 2 letters, the only function. So it's a lonely function, has only 2 letters. It feels very alone. Rules for the logarithm, which follow from the rules for the exponentials. So what we have, for example, so we have the log of x times y is the log of x plus the log of y. So that's the reason why logarithm tables or this toys. This is actually my grandfather's logarithm rule, or which allowed to make computations. So it's based on the fact that when you take the multiplication becomes the addition in the log scale. It's a pretty cool thing, historically very important, because this allowed to compute things very much more efficiently, also in astronomy. So the logarithm is very important. So that's one of the rules also, or we have the log of e to the x is equal to x. So this is equivalent, right? And then we have this rule here. And so these are the most important rules about the logarithm. But very important is also the log of 1 is equal to 0. And the domain of the log is just always the positive real axis. Domain of log is the positive real axis. So it doesn't include 0. It's not defined at 0. So it has a kind of an asymptote. We call this also a vertical asymptote here. And it goes to infinity. Slowly, but it goes to infinity. So the most important thing is that you know the definition of the trig functions, and it's all given in a picture here. So what we have is, if x is here, given as an angle, then this is cosine x, this is sine x, and you can also read off tangent x if you like. So tangent x is sinus x over cosine x, and it's all based on so let me just the cosine x here, so that's the cosine x here. So it's the cosine is the adjacent over the hypotenuse. This is the hypotenuse, this is the adjacent, and sine is the opposite over the hypotenuse, and tangent is the opposite over the, so this over that, that's the same thing than this over that, and that's 1. So this whole thing, this is tangent x here. You can read off tangent x. It's the slope which belongs to that angle. Very important. And then we have sine x here and cosine x. So cosine x is here, and this is sine x. Just actually put it here. Sine x. So these are the definitions, and then we can draw the graphs of these functions. So the sine, let's draw first the cosine x here, because that's what we have here is cosine x. It is, when x is equal to 0, it's 1, and so it goes to 0 and then goes up, out. So this is, so it's pi half. The cosine is 0 at pi half, and then at 3 pi half again. At pi it is minus 1. We got pi, then we are minus 1 here. So this is the cosine x. So this is fx is equal to cosine x. And then we have the function f of x is equal to sine x, which I made orange here. So this is the function here, so it kind of goes like that. So at pi it is 0 again. So this is sinus x. Very important function too. So at pi half it is 1, and at 3 pi half it's -1, and then at 2 pi it's again the same value. Also here at 2 pi we are again at 1. So this is 1, this is -1. So here it's -1, -1. So that's the sine and the cosine function, and then there is the tangent function. Let me draw it here. So minus pi half to, usually it is drawn from minus pi half to pi half, which means here on this part, so what we have is, I'll make it blue, this function here. It's like that. So this is tangent x. So this has two asymptotes. So there are asymptotes here. And it's clear because when cosine x is equal to 0, you get the problem. Cosine x is equal to 0 means at pi half. So these are roots here, or minus pi half. So when you look at that and you divide by 0, so you go to infinity here. So that's why the tangent is usually drawn like this. So this is these are the trig functions, and then there are some functions which I try to avoid them, like the secants and the cosecants. So the secants functions and the cosecants functions. So x is equal to 1 over sine x, and this is 1 over the cosine x. And then there is also the cotangent function is actually used often. Cotangent x, that's just cosine x over sine x. That's actually quite a frequent. So you can be a little bit. You can actually avoid these functions here. But the cotangent, you can in principle avoid. But I would keep that one. The tangent is very important. Tangent and cotangent are both important. Sinus x and cosine x are extremely important. So keep this function in mind and make your own kind of little sheet with the properties of these functions. And then we can also invert the function. In this lecture we also talk about functions, the inverse of functions, and let's just look at a few examples how we get the inverse of a function. So the inverse of a function is just graphically obtained by flipping along the diagonal. So let's do that. So in order to invert the function, we have to pass a test, which is the horizontal line test. For example, if you take this function x squared, f of x is equal to x squared. And so if you look at the function also on the negative thing, we cannot invert it everywhere. But in order to invert it, what we do is we just draw the diagonal and then flip it around. And in this case, we get just the square root function. So this was f of x here. And the inverse function, that's we also call this f inverse. It's the inverse function. And it's called square root. So that's one example. Another example of an inverse function is log is actually the x inverse. So it is important that we actually, when we write something like that, that we are not thinking about 1 over x. So that's something completely different. So the log of x is the inverse of x of x. And it's defined only on positive x, because the x of x has no 0, it doesn't, also not negative. So this is a example of a inverse function. And then another example is maybe the arctan. So the arctan, usually we write arctan and not tan inverse. So that's the arctan, and the arctan is obtained by, we have just seen the tangent function, and the tangent function was like that. Just we flip it, so when we flip it around we get this. So that's the that's the graph. So this graph here, and it goes from minus pi half to pi half. So this function has what one calls a horizontal asymptote here. So that's the arctan. Let's look at the arcsine function. That's a little bit a trick here. So let's just see. First of all, we have to decide where we invert the function. So the sine function we have seen goes like that. That's the sine function. So we can invert it from minus pi half to pi half. So if you look at the sine function from minus pi half to pi half, we get something which is invertible. So sine of x is invertible from the domain minus pi half to minus 1, 1. Right, so that's the minus 1, 1. So it starts from a point between minus pi half and pi half, and ends up between the point from minus 1 to 1. So if you want to find the inverse function, you have to flip that at x equal to y. So you have to flip that, and then you get a function which then looks like that. It's kind of something like that. It's kind of hard to kind of get your hand on it. So let me just draw that again. So that's the arcsine. It goes from minus pi half to pi half, and then from minus 1 to 1. So let me just draw that again. So it's kind of a little bit a trick. A computer is really your friend when you are doing plotting. So there's Wolfram Alpha, there's Desmos, there are lots of online tools to plot things and make use of them. So in this case, let me just draw again this arcsine function. It goes from minus 1 to 1, and then it goes from minus pi half to pi half. And so what happens is, so I had it red here. Let's make it red again. So it looks somehow like that. So this is the arcsine function. But you see, it's a little bit more tricky, because we first of all have also decide where we want to invert the sine function. And between minus pi half and pi half is a natural choice, right? Minus pi half and pi half. There we have an invertibility, because we have this horizontal line test. It only intersects at one point. If you would take the function from 0 to pi, for example, we would intersect at 2 points, and then it would not be clear, right? So this point has the same y than this one. So from this we don't know where to go. Shall we go here or shall we go here? So it's not invertible on a larger interval here. But it's naturally invertible from the interval from minus pi half to pi half.